Okay. Well, welcome everybody to the 7th lecture in this series. Can you believe 7th? And we're going to talk a bit more about braids and representatives for this one. So let me get some notes up. Can that be seen?
Mm-hmm.
Can you see that, Lou?
I see it.
Good. I think people are trying to get in, which is, I better let them all in so I'll stop sharing. I must work out how to do that. 17 people are waiting. Admit all. Okay, they've all been in. Okay, welcome everybody.
Hi.
Oh, hi Dale.
Hi, Roger.
Oh, you missed my tribute to Kraftwerk. I'm sure Steve knows who Florian Schneider is.
Was.
Today.
Okay, but this is about mathematics.
Lorenzo.
So I'm going to share now, and if no, this is wrong. Let's make this full screen. Okay. Right, I hope everybody can see that. Is that a resounding yes?
Mm-hmm.
Okay. So we're going to talk about some representations of the braid group. Now, we talked about the Bourau representation last time. And so I just quickly whiz through that. We take this matrix here, sigma 1, which has determinant minus t, and we include it in the usual way into an infinite matrix, and then we define, we have the Bourau representation is given by this. So sigma I goes to this matrix sigma I. And then a little bit of chat. Nobody's come up to tell me if anything new has been proved. The Bourau representation is not faithful. In other words, there are non-trivial braids which under the Bourau map go to the identity matrix. Okay. And the representation of Bn is faithful for n equals 1, 2, 3, but B4 and B5 remain open as far as I know. Okay, so, and the Bourau representation is interesting because it gives rise to the Alexander polynomial, and later on we'll show how that works. Okay, now we left with the looking at the Hecke, the representation onto the Hecke algebras. Okay, and that's how we get the Jones polynomial and the homflypt polynomial. And as I said, if we put in a quadratic relationship to make Bn into a ring, And if you look carefully at this, you see sigma I is positive crossing. P is just a scalar times the identity, and this is Q times the sigma I inverse, which is a left-handed crossing. So that's just like a skein relation. We want to make this map sigma I to Q into a homomorphism, and you can quickly check that this implies that P has to be Q minus 1. Okay. Right, so A is the ring of Laurent polynomials in Q with coefficients, the integers, and the Hecke algebra Hn is generated by 1, T1 up to Tn, and its relations are, well, Ti and Tj commute if they're far enough apart, just like the braids. And similarly, we've got the Yang-Baxter equation here for if they're close together. But now we have Ti squared is Q minus 1 Ti plus Q. Remember, P had to be Q minus 1 in order for this to be, for the map from Ti to Q to be a homomorphism. Okay, and Ti inverse is given by that formula there. And we get natural inclusions. H denotes the direct limit of the Hn. And right, what do we got? So here's a lemma that as an A module, Hn is generated by the monomials in T1 up to Tn minus 1, with at most one occurrence of Tn minus 1. And this lemma may be proved by induction on N using the relations of Hn. So we're going to slightly improve this result. So consider the following set of monomials. So sigma 1 is 1 and T1. Sigma 2 is 1, T2, T2, T1. And generally, sigma n minus 1 is 1, Tn minus 1, Tn minus 1, Tn minus 2, blah, 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 down to T1. Okay. And as you see, each of these monomials has at most one occurrence of Tn minus 1. Okay, so here it's just on its own, here it's combined with Tn minus 2, and so on. And this is just the product of a lot of them. And then sigma I, we get from sigma I minus 1 by adding the identity element and Ti times sigma I minus 1. So a monomial M in the form M1 up to Mn minus 1 with Mi in sigma I, okay, is said to be in normal form. So, and if you think M1, so M1, for instance, belongs to sigma 1, which is just 1 or T1. There's two ways of choosing M1, and then M2, it belongs to this set, so there are three things there. So there are, anyway, what I'm trying to say is the number of ways of choosing M is 2 times 3 times so on times N, so which is N factorial. So we've got the following lemma. Monomials in normal form generate Hn. Once more, this lemma may be proved by induction on N, so that's an exercise for the reader. As an easy consequence of the last lemma, we derive that the dimension over A of Hn is less than or equal to N factorial. I have no idea why there are 2 full stops there. I suppose it's the end of a sentence. Okay. In fact, we want to show that the dimension is actually equal to n factorial. So we have to prove the inequality the other way. To achieve this goal, we have to make some preparations, and it's quite interesting algebra. You may not agree, but I think it is. So let's have a look. So Sn is the permutation group on n symbols, and Si is the transposition of the ith and I+1 symbol. Denote the free A module generated by the elements of the symmetric group Sm by A Sm. Well, there are n factorial elements in Sn, so the dimension is n factorial. Now we're going to define a left operator, Li, in endomorphisms of Asn with the following rule. So Li of pi, well, because it's a left operator, this is what we expect. We multiply pi on the left by Si. And that's fine if we don't get any cancellation. In other words, if the length of Si times pi is bigger than the length of pi. If it isn't, then we change the definition to this, okay? And now we've defined Li on the permutations, and then we extend it linearly to an endomorphism of Sn. It's easy to check. Always be alert when you see words like "it is easy to check." But I think in this case, it really is easy to check that Li squared is Q minus 1 Li plus Q. For instance, you see, if you multiply by Si, and then you if the length increases, in other words, there's no cancellation, the next time you do it, when you multiply by Si, it decreases in multiplication. And so you get this, and then you know, this comes out quite easily. I have looked at it. Okay. Well, and then we define a right action, Rj, same sort of idea, except now we're multiplying it on the right by Sj, and that's if, you know, there's no cancellation. So if the length of this word increases, and then the same sort of gizmo here. Now the multiplication is on the right here of pi. Here it was on the left, okay? So, and then we extend linearly. As in the case of Li, we easily calculate that this is true. This Rj squared is Q minus 1 Rj plus Q. Moreover, we get the following lemma, and this is the really interesting bit, which shows that the left and the right action commute. So we have Li Rj is the same as Rj Li. Okay. And okay, there's 6 cases to be considered to verify this fact, and 1 to 4, they're all right, they're pretty easy. Now, the 5 is a little bit tricky, but we can do it. We can do it. So this just says, if it's the case that the length of Si pi Sj is L pi, but that the length of Si pi is greater than the length of pi, and the length of pi Sj is greater than the length of pi. Well, so let's have a think about what that means. So that means there's no cancellation when you multiply on the left by Si, and there's no cancellation on the right when you multiply by Sj. So if you take the strands in pi, the two strands where SI hits pi, they will be untangled, and they're the same with multiplying on the right. The strands on the right of pi, when you multiply on the right, when you trace them back, they will also not be crossed, okay? But we also have that the length of SI pi Sj does decrease, okay? It's the length of pi, which must mean that in the inner workings of pi, Si and Sj have to cancel. They go into pi and they cancel, so you just get the length is unchanged. I'm going to try and do a little drawing, if this is possible. More. Come on.
Roger, can I ask a question?
You may, Dale.
If you take a product of two permutations, what order do they go? Let's say it's A and B. A, B, do you do A first and then B, or B first and then A?
Well, it doesn't really matter, Dale, but let's pretend we do B first and then A.
Okay.
But
So
I don't think
similarly
it
for
makes any
braids.
difference to the argument.
Yeah.
Okay. I can't seem to work out how to annotate this. You'll just have to put up with it, I think. Let's go out of stop share and back in again. So, right, share. So, should be able to annotate this, but I can't see. It's very. Anyway, why don't I do it on a piece of paper and show you? So I'm trying to get you to see what the picture is. So it's a simple picture, so let's stop sharing. And can you see me? Some reason I've got Stevie here right in the way. I don't know why. Does you want to chat? No. Okay.
No, I'm going to move outside. It's so hot.
Now I can see Dale. Right. Gallery view.
Nope.
Speaker view. Okay. Can you see this?
Yes.
Okay.
Yes.
Do you get the picture? The crossing of SI on the left cancels in the middle of pi, you see, because the strands joining them form a band. Okay? That's why it works. Okay. So go back to share. So this is case 5, okay, where the length of SI pi Sj is equal to the length of pi. In other words, SI and Sj must cancel within the innards of pi. And my little drawing, I hope, illustrates why that is true, because it doesn't, SI doesn't cancel on the left with pi, and Sj doesn't cancel on the right with pi. So, and then case 6 is similar, so we won't go into that. Okay. So anyway, what are we trying to prove? We're trying to prove that Li, the left multiplication by any Si, and the right multiplication by Sj, they commute. Okay. And there's a reason why we want to know that, which will be revealed very shortly. So I've said here what I thought was I tried to do the picture. Okay. So we've got this Li Rj pi is Li pi Sj, which is this. Because yeah, so because it reduces, it's this, which is, and then Si pi, because you can carry the Sj all the way through pi along that band, which I illustrated so it becomes an Si, all right? And then you've got this, which is Rj times Li pi. So that's one example of how they commute, and the other cases are easy. Okay. Right. So we've proved, now we want to prove these relationships for the Li. So let pi be an element of the symmetric group Sn, and let pi have length k. Okay, so we'll write pi as Si1 up to Sik, and so that's in reduced form. So that means that pi is Rik up dot 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 Rij of 1, okay, because we're multiplying, I think that works, we're multiplying on so we, for instance, Ri1 of 1 is Si1, and then Ri2 of this would be Si1 times Si2, okay, and so on, up to Sik. Right, okay, now we put R equal to this product, this operator here. So we can compute for I minus j greater than 1, Li Lj of pi is Li Lj R of 1. Now we use the fact that R commutes with all the L's. So we take the R over to the left, and then we get R of Si Sj, which is R of Sj Si. And this is R of Lj Li, and then R commutes, and then we get Lj Li pi. So so this is for, you know, because I and j are far enough apart, you see, Si Sj is the same as Sj Si. And we're using the fact that this R commutes with the L's. Clever, isn't it? Okay, and you do something similar to show that that Li Lj Li is the same as Lj Li Lj. This, but this last one, this here, we've already shown that, so we don't need to prove that again. So what does that mean? That means that there's a well-defined algebra homomorphism rho from Hn to endomorphisms of a Sn with rho of Ti equals Li, okay, because that satisfies all the conditions, all the properties of the Hecke algebra. Right, now we take a so we take M to be the set of monoids in normal form. And we've arbitrarily ordered them up to n factorial. So this is a basis for ASN because we've got a homomorphism. Hence, the set of monomials M is linearly independent. Thus, the dimension is greater or equal to n factorial. But we already know that it's less than or equal to n factorial, so we obtain the fact. What we wanted to prove that the dimension of this algebra is n factorial. Good. So this means that the monomials in normal form actually form a basis of Hn. We can conclude that any element C in Hn plus 1 can be written in the form C equals A plus sigma AI Tn Bi with the A, the Ai, and the Bi in Hn. And this representation is unique up to equivalence. We can move the y plus the Tn if y is in Hn minus 1. Okay, so we have this theorem that Hn plus 1 is Hn. Okay, this is corresponding to the A here. And then Hn tensor Hn, the tensor being over Hn minus 1, because the Hn minus 1 elements commute around it. So that's what that little symbol means on a tensor product. Okay, so that's progress. Now, we want to define a trace function. Okay, now what is a trace function? A trace function is an alinear map which satisfies tau of AB is the same as tau of BA, just like the normal trace of matrices, the sum of the diagonal elements. As we know, trace of the product of two matrices doesn't matter which way around. We multiply them, the trace is the same. And then we call it normalized if tau of 1 is 1. So we want to define such a trace. And there is a unique normalized trace function tau from H to this algebra, well, this ring of Laurent polynomials, and it's defined by tau of A TMB, okay, is Z times tau of AP. So A and B now will belong to Hn, okay, but Tn, of course, belongs to Hn plus 1. So we're introducing this factor Z here, and then we assume by induction we know how to work out tau of AB. Okay, so we extend it now to Hn to Hn plus 1 by this formula here. Okay, so this is a unique way we can extend it. We only have to show that it is a trace function, that tau AB is tau BA. So a bit of checking here, and then there's various cases. We not only need to show that it's true for monomials in normal form, and there's a couple of cases. Supposing M1 is this, and then this is that, Z times that, this is that, is that, is that. And if they both contain Tn, then we use two general identities that tau mu1 Tn, mu2 Tn is tau of that, and that were monomials, and we assume these are true, then we go on like this. So there's a little bit of checking to do, which I won't go into now. Right, so we've got this trace. And we've got a representation of Bn into Hn, which sends, of course, the generator sigma I to Ti. And then we compose this with the trace function. We have a function from Bn to this ring of polynomials in Z. Right, we want to use this trace function to define an invariant of oriented links. To do this, we briefly recall the theorems of Alexander and Markov, which I mentioned earlier. Any braid B can be made into an oriented link or not or whatever by closing the braid. Done all that. The theorem of Alexander asserts that any oriented link may be obtained in this way. Okay, that is, given a link L, there's a braid B such that the closure of B is isotopic to L. And so that's, as I mentioned, this is something like surjectivity of the closing operation. Markov's theorems deals with the kernel of this operation. And here we have two braids B and B dash become the same link after closing if and only if they can be related by a finite sequence of Markov moves. So in other words, if we've got product two braids, we could switch them around. B1 times B2 is equivalent to B2, B1. And B1 is equivalent to B1 times Sn, either sign, if B1 belongs to Bn. So remember, Sn doesn't belong to Bn, Sn belongs to Bn plus 1. Okay, so there's a natural inclusion of Bn in Bn plus 1. So you know, this multiplication here is is what we have.
You mean sigma n?
Oh, I do. Well spotted, Dale. Okay, that S should be a sigma. It should go Greek. Sorry about that. I didn't see that. Okay. So we've got a way of producing link invariants. If F is a braid invariant, we can define F hat by setting F hat of L to be F of BL. BL is supposed to be any braid whose closure is isotopic to L. Alexander's theorem assures that F hat is defined for any link L, but not necessarily the same invariant. This invariant F will be well defined, a link invariant, if and only F is invariant under Markov's moves. Okay, so that's the next thing. Oh, and I should say that everyone has their own favorite proof of the Alexander and Markov theorems. Naturally, my favorite is the one I did with Andy Bartholomew. And it's in the archives if you want to have a look at it. It's not only does it for real knots, which that's the only thing we've been considering, but for generalized knots of a certain time. In this paper, which will prove analogs of Alexander and Markov results for classes of generalized knots, which were called regular and normal. Any knot theory which has the R2 move, that's the second right-of-isoter move, is regular, as we saw, because we saw the proof of Alexander's theorem using the right-of-isoter 2 move. I won't say what normal is at the moment, but classical knots and virtual knots are examples of normal theories. What are virtual knots, I hear you say? Well, we'll come to that in a minute, and I'm sure Lou will also do that. Is that not right, Lou?
Certainly.
Certainly. Good. Okay. So anyway, get back to here. We want to make the trace T defined on braids into a link invariant. By the property of trace functions, T is already invariant under the first Markov move, okay? It is not yet invariant under the second Markov move. With the help of a normalization factor, this can be achieved. So define E from Bn to Z by E of sigma I equals 1, okay? This is a well-defined group homomorphism. In fact, the abelianization of Bn. And now we put in a really interesting, complicated formula. The homflypt polynomial is the link invariant V defined by this. So we've got Z to the minus n plus E of B, this number here, minus 1 over 2, times Q over 1 plus Z minus Q, and T of B is the trace of B. Okay, well, B is any braid whose closure is isotopic to L.
N.
Well,
What's N? Braid index.
okay, so that works because this takes into account the rise you get from the second Markov move. And now I think Scott was asking about how this is related to the formula for the homflypt polynomial given by Lou, and you should be able to get it from this. If you put lambda equal to the square root of minus z over z plus 1 minus q, and mu equal to I times q 1 over the square root of q minus the square root of q, then you get this skein relation. Okay. So you should be able to work out how that relates to what Lou said. Okay, now, so that's the way we've now shown how to define the homflypt polynomial from the Hecke algebra. And nice proof, I think. I'm now going to put up a little table. I mentioned, I wonder if I can make this, what happens if I do that? Ah, okay. Okay, can you see that all right? Remember, we started off a diagram with a shadow of a knot, okay? And the double points cross in the shadow. And in order to get, say, a real knot, we have to lift up the arcs either in this positive way or this negative way. And having defined this diagram, we can then, we've got the three Reidemeister moves here, R1, R2, R3, which are allowed on in the real case, or what I could call the classical case, perhaps, the classical case. Now there are, I don't know why I've got this green line here. Anyway, so that was, but there's lots of other things here which you might wondering what's going on? What's going on? What is all this stuff? Well, there's also something called a virtual crossing, and Lou neatly says that it's virtual because it doesn't actually have any geometry. It doesn't really exist. But it, I'll say why we introduced this in a minute. Okay, but there are all other things as well. There's something called a doodle, which satisfies R1 and R2, but not R3. So this table really is like a list of rules in a dodgy bed and breakfast where everything is forbidden unless it's expressly allowed. Okay, so R3 is blank here, so you can't do R3 with a doodle. Anyway, I will maybe come back to that later, but I want to say why we get virtual knots. Okay, so one way of they're invented is, so let's look at the trefoil. This is the left-hand trefoil, and this is represented by an embedding of a circle into space. Okay, so it's knotted in that fashion, and then it's projected onto the plane, and wherever it has one of these three double points, we take this circle and we say, well, we're going to join up these points, which are double points on the circles because they go to the same point, by an arrow, and the arrow points down from the top to the bottom. Okay, so from the top, from the overcrossing point down to the undercrossing point. So that's just a convention. Okay, so that's the way the arrow goes, and it's got an R bar on it here to say that this crossing is a negative crossing. Okay, all these three crossings are negative. So and you can see that that is indeed the case. So that's a chord diagram, and you can do it for links as well. These arrows here appear to cross in the center, but that's just an illusion. The arrows are disjoint from every other arrow. Okay, and they just have endpoints on the circle. And so every knot has a chord diagram, right? Every knot diagram has a chord diagram. Here are two chord diagrams which don't correspond to classical knots. Okay, so if instead of having three arrows here, you have two arrows, both annotated by R, meaning they're positive crossings. You can't, you can try, if you like, on a piece of paper to realize this is a knot diagram, and you can't. The same thing here, you've got, this is a knot with two components, and they're joined. I haven't bothered to put an arrow in here. It could do, but it's a flat crossing, and once again, it can't be done. So what do? Well, we do something which at first sight seems a bit of a blunderbuss solution, right? So we just say, well, we can't do it unless we allow things to cross which aren't there. Okay, so for instance, to realize this, okay, we've got two positive crossings here, and we can't join this up to here without crossing this arc here. So we say, oh yeah, okay, well, we'll do that. And then we've got this virtual crossing here, and that's the same here with this one. If we try and realize it, we've got one flat crossing, because F the flat, and then in order to complete the circle, we have to put in a virtual crossing there. Okay, now So you might say, oh yeah, well, brilliant. You've introduced something, and just so you can make sure that every chord diagram can be realized, but with virtual crossings, big deal. Well, in fact, and this is a marvelous thing, that you can replace this virtual crossing by a little handle on the plane, so that you now have a knot diagram on a surface. So there is sense in this, is that knot diagrams on a surface can be realized by these virtual knots. Okay, so now that's trying to give you an indication of things, why there's more to life than classical knots. There are various other things, I've got them here. There's flat knots, there's doodles, there's regular homotopy, virtual knots. They obey the same rules as the flat knots, all R1, R2, R3, but they dominate everything. That's that little symbol there. I won't say what that means, but that's the power of virtual. Welds are similar, but welds are dominated by real crossings. Anyway, and there's lots of other things as well. Singular knots, and they have an inverse. Okay, but I'm not going to say any more about that now, and I think I'll stop there. Stop sharing. Del Rolfson has entered. I thought you were already in. Anyway. So, right, okay. Are there any questions?
Could the notes be posted before lecture next time?
Sorry?
Could the notes be posted before lecture next time?
They will certainly be posted, because I have recorded this. And so I'll put that on YouTube. I think, Lou, you were going to redo your talk?
Yes, I will be re-recording the talk I gave last Tuesday, and probably send it to Roger sometime late tonight.
Brilliant. Okay.
But
So
I don't expect myself to post notes that are correct for the next lecture, but I'm always posting my notes, so they're somewhat in an intermediate stage before the lecture happens, and then they get corrected a little further after the lecture.
Okay. Well, my next lecture.
I had a
sorry.
question. I had
Yes,
a question during your talk. It seems like some of the proofs could be simplified if you had actually drawn some pictures there.
They could have been, but
Yeah.
for some reason, my annotation thing didn't work. I don't know why. It's there's always got to be a technical glitch. It's one of the rules of these lectures.
Sure. Really appreciate it, though. Thank you.
Oh, okay, Scott. My next talk, I'm going to go into three-manifold theory, I think, and how that relates to knots. So, if there are no more questions, I will finish this meeting, and thank you all for attending.
Thank you.
Bye.
Thank you. Thank you.
Thanks, Roger.
Thank you. Bye-bye.
Bye.